Why'd you skip geology class?
What's so interesting about rocks anyway?
Stop right
I
there.
want to introduce something. It's that voice.
E.R. Science Brigade.
Who are you?
We're the cry for knowledge.
And we've come to answer.
Huh? You're crazy. Let's get out of here.
You're not going anywhere before you learn about geology and about the interesting stuff about our Earth. Let's start with what are rocks and minerals.
Well, rocks are formed from consolidated materials such as grain or minerals.
While minerals are defined as a naturally occurring crystalline solid of definite chemical composition, you can also determine a rock's chemical structure by checking the following, such as its magnetism, electrical conductivity, radioactivity, and reactivity. Minerals don't just sit there looking pretty either. They actually have various benefits that are used for various things in our society. These helpful minerals are classified into three. Ore minerals are a type of rock which can be sediment which contains valuable metal inside. Industrial minerals, a mineral with economic value. And gems, a precious stone which is engraved, cut, or polished. Ore minerals are used to create the various metals we use for manufacturing technology, construction, and many other endeavors. These include chromite for chromium, pyrolusite for manganese, and magnetite for iron. Industrial minerals are also quite useful, but they are not used for their capability to turn into metals like ore minerals. Instead, they are used for their specific chemical and physical properties. These include graphite, which can be used for pencils, crucibles, and electric motors, bartite, which can be used for paint, X-ray shielding, and rubber, and various feldspars, which can be used for ceramics, glassmaking, and paint filler. Gems are usually what you think of when you see or hear minerals or crystals. These minerals are used for cosmetic purposes and jewelry accessories because of their brilliant beauty. These include diamond, topaz, emerald, a variety of beryl, amethyst, a variety of quartz, and garnet. Moving on from minerals, now let us talk about rocks. Mainly, there are three specific types of rocks, one being igneous rocks, the other sedimentary rocks, and the last one metamorphic rocks. Now let's start with igneous rocks. Igneous rocks are formed from solidification of molten materials such as magma. Some of the characteristics of igneous rocks are: igneous rocks do not include any fossil deposits. Most igneous forms include more than one mineral deposit. They can be either glassy or coarse. They usually do not react with acids. The mineral deposits are available in the form of patches with different sizes. There are two types of igneous rocks. Intrusive igneous rocks are rocks that crystallize below the Earth's surface, resulting in large crystals as the cooling takes place slowly. Extrusive igneous rocks are rocks that erupt onto the surface, resulting in small crystals as the cooling takes place really quickly. Some examples of these igneous rocks are granite, basalt, and pumice. Now let's move on to sedimentary rocks. The definition of sedimentary rocks, when you Google it, are formed by accumulation of the fragmental material derived from pre-existing rocks of any origin, as well as the accumulation of organic material or precipitated material. Sedimentary rocks undergo a process called sedimentation, which is when organic and mineral particles settle and combine to make sedimentary rocks. Some examples of sedimentary rocks are limestone, chalk, sandstone, shale, and coal. There are also stratified rocks, which are a type of sedimentary rocks which have been stacked on top of each other over time due to erosion or other natural effects, but we will go to a more detailed process in a later segment. Lastly, we have metamorphic rocks, which occur as a result of high pressure and high temperature and chemical activity of fluids changing the texture of minerals, which basically means that in the presence of high temperature or pressure, such as underneath our Earth, it can cause rocks to sort of turn liquid even though they are still keeping their solid form, and after that process, they turn into metamorphic rocks. Some examples of metamorphic rocks are marble, gneiss, slate, and quartzite. Isn't it interesting that the materials I said are used a lot, especially granite, to make sure buildings have increased stability?
Oh right, I forgot about the rock cycle.
What?
Don't get confused. It doesn't involve cycling. Now back to our topic.
The rock cycle is a process that all rocks undergo, but for some, it may seem improbable for them to do a full cycle.
The rock cycle has 4 processes. 1 being magma, 2 being igneous rocks, 3 being sedimentary rocks, and then lastly, metamorphic rocks.
Some rocks can entirely skip some of the processes. It just depends on the environment that the rocks are situated at. Now let's continue with exogenic and endogenic processes.
Well, it all starts at the top.
In a mountain, let's say Himalayan mountains, well, before they were volcanoes, but in due time they did turn into mountains. Anyway, after it erupted, some leftover magma. It hardened and turned to igneous rocks. These igneous rocks stay in this stage for a while, but slowly get eroded by rain and any other natural forces. Once it has fully eroded, it just falls down from the mountain and lands in the water or a depression, where it will be trapped and compressed, which turns into the sedimentary rocks. After the sedimentary rocks stay in between the bottom of the ocean for a while, then eventually they are affected by the Earth's temperature, which will cause it to change into metamorphic rocks. After the metamorphic rocks stay underneath for a while, it sort of changes due to the high temperature. It causes the metamorphic rocks to melt and later form into magma. And this magma later gets inside the volcano's core, and the magma just sits in the volcano's core until it erupts, in which magma is poured out of the volcano. After a while, it will cause the magma to crystallize and turn into igneous rocks, after which the igneous rocks get affected by weathering, again repeating the cycle.
You're crazy! Yeah, someone please focus! Wait, nothing to the rocks.
No! Those are not rocks.
What's the difference?
Well, the one way to determine whether a rock is to look at its chemical and physical properties. An easy way to identify is to check the appearance. A mineral has more of a luster, pointy outside, and colorful appearance, while rocks have a rough, sometimes smooth surface, while also having a solid state of matter.
Do you understand now?
Wait a minute. If those are rocks and these are minerals, then what is the Earth?
Well, the Earth, mostly where we're standing, is called the crust.
The crust is where we humans and any other living organisms live, and there are more layers to our Earth, like the crust, the mantle, the outer core, and the inner core. Let me explain these layers on the Earth much more detail. As I said, the crust is the layer where all living organisms live or reside, while the mantle is the largest layer of the Earth, almost covering 84% of the Earth, while also being the most sturdy and hard to dig through layer. The outer core is the place where hot iron is located, such as iron and nickel. Lastly, we have the inner core, which is the most hottest place, which is similar to how hot the surface of the sun is. For reference, the sun is 10,000 Fahrenheit hot, while the Earth's core is 9,392 degrees, which is pretty hot when you think about it.
So now that we've discussed the layers of the Earth, where were we?
Hey, I'm a big fan of moving too. Let me clue you in about rock movements. Okay, let's move on to the even more interesting details about rocks.
I can't think of any more interesting things about rocks. Let's find out then, shall we?
Before we continue, can you guess how rocks can be more interesting?
I can't think of any.
Well, that introduces us to our next topic, which is the movement of rocks.
Oh, I just remember having this lesson in our biology class almost a week ago. From what I remember, there were 3 types of stress in rocks, which are tension, compression, and shear. Although I vaguely remember what they mean, could you please enlighten us?
Well, sure thing. Imagine the Earth's rocky puzzle pieces are playing a wild game of push and pull. Compression is like a tight squeeze that squishes rocks together. Tension is when they're tugging apart, and shear stress happens when those giant tectonic plates do a funky dance, twisting and changing the shape of the rocks as they rub against each other.
What would happen to the rock once the stress leaves?
Well, rocks have a few tricks in their sleeves in the aftermath of the stress. They can either revert back to their original shape, which is called elastic deformation, plastic deformation where it refuses to budge or return to its original state, or fracture, where the rock just makes a dramatic snap.
Based on what we've learned up to this point, when the Earth's plates feel pressure, they're not just sitting still. No, they start to shake, which leads to 3 distinct movements. 1. Convergent plate boundaries. Picture plates colliding head-on, like 2 sumo wrestlers in a fierce face-off. The outcome? Mountain ranges rise, and mighty earthquakes shake the ground. 2. Divergent plate boundaries. Now imagine plates going their separate ways, like a superhero splitting the ground as they soar through it. This leads to the birth of new land, like volcanic islands and ocean floors spreading apart. 3. Transform plate boundaries. In this corner, plates slide past each other, like slick sports cars racing on a track. The result? Earthquakes of epic proportions, fault lines, and dramatic landscapes. Oh, I also remembered, from what I learned, that the ocean seafloor does split and spread. But I forgot how the concept goes again.
Don't worry about it, I remember it. The basic concept is that due to the increased temperature of our core, the mantle starts to split apart, causing the seafloor to spread out.
Is that all? I remember it including ridges and trenches, and whatever stratosphere and lithosphere is.
Whoa, slow down. Let's tackle this one at a time. Well, first, trenches are caused by tectonic plates colliding, causing a plate boundary to be created, while ridges are underwater mountain ranges that crisscross with each other and is usually formed in zones with rising magma where 2 plates are moving apart.
Oh, I see. What about a stratosphere and lithosphere?
Well, the stratosphere is the lower part of the lithosphere, which is a solid layer of rock that has so much pressure and heat that rocks flow like a liquid. The lithosphere is the rigid layer of the Earth consisting of the crust and solid outermost layer of the upper mantle, which is composed of rigid blocks or plates.
How about ocean basins?
Ocean basins?
I can explain this one. Ocean basins are formed from the stretching and splitting, drifting of continental crust by the rise of mantle material, and magma, which is directed to a crack that creates a new oceanic lithosphere.
Oh, I see. So basically, it's our ocean floor getting stretched and the contents of the Earth spewing out, such as magma or some of the mantle itself.
Exactly. You know, all this talking about the plates moving underwater makes you wonder, how do the movements of the Earth influence these objects to form, such as faults, faults, trenches, volcanoes, rift valleys, and mountain ranges?
Okay, first, why specific? And second, I have the perfect answer for that. Well, have you noticed anything with volcanoes, trenches, etc.?
Well, no, not really.
The common similarity is that all are made due to the ocean spreading, colliding, and compression.
Oh, what happens after that?
After the plates collide, spread, or compress, the liquid called magma escapes from the mantle.
Huh? If plates and rocks can move, then this may be the reason for the continental drift too.
Well, yes, your hypothesis is correct.
But before we continue, what really is the continental drift theory?
This theory was a precursor to the modern understanding of plate tectonics, which explains how the Earth's lithosphere is divided into several large and small plates that move and interact. There is a lot of evidence that supports this theory, and those are jigsaw fit, fossil evidence, evidence from rocks, evidence from climate change, and the evidence from magnetic polarity. Now, let's break down the evidence piece by piece to make it more engaging. Imagine this. Some continents and countries seems to slot together like a perfect jigsaw puzzle. The classic example, the east coast of South America and the western part of Africa, nature's own game of connecting the dots.
Well, now, let's move on to the second piece of evidence in this puzzle, which is fossils. Paleontologists have stumbled on a real head scratcher here. They found the same predators fossils on different continents. But here's the kicker. These ancient creatures weren't exactly equipped for world travel. It's like they had a pretty basic GPS system, and yet they ended up all over the place.
So, how did they get there?
Think of it this way. Imagine all these ancient creatures living together in one big neighborhood. As they died off and turned into fossils, the land they were buried in slowly drifted apart. Take Sanagnotus, for instance. It couldn't fly or swim, yet its fossils ended up in both South America and Africa. Even though those continents are now separated by water, it's like a story of land masses playing a game of musical chairs over millions of years.
Oh, so therefore we can conclude that two continents were once together and the fossils buried beneath these lands were separated as the continents broke apart.
You're correct. Now, for the next piece of evidence, think of it as a global rock concert tour. Scientists have discovered mountain ranges in different parts of the world that have the same look, rock compositions, and age. Turns out, these mountain ranges were once connected, but then they pulled a rock and roll breakup as continents drifted apart. Take the Appalachian Mountains in the eastern United States and Canada. They used to be BFFs with their mountain ranges in the eastern Greenland.
If you look closely, they look similar, an indication that they may have been once together.
Now, for our next piece of evidence, picture this. Antarctica, the icy realm of penguins and polar bears. But guess what? We've found cold there. Yes, the kind that usually form in the warm, swampy places. It's like discovering a tropical oasis in the middle of the snowstorm. How did that happen? That's the climate change enigma we're diving into.
Now picture this. Antarctica used to be a tropical paradise millions of years ago, complete with swamps and natural coal production. But as time ticked and on the continents shuffled around, Antarctica moved south, turning into an icy freezer. Now all that coal we find there is like a souvenir from its warm partying past.
Oh, now it makes sense.
Magnetic polarity evidence is the conclusive factor. Initially, magnetic crystal in newly formed volcanic rocks aligned with the North Magnetic Pole. However, in a specific exploration, scientists discovered these rocks, but none of them pointed to the current North Magnetic Pole. Instead, they varied in direction and came from volcanoes of different ages. Interestingly, despite having the same age, volcanic rocks from other sources pointed in a similar direction. This magnetic crystal initially aligned with the North Magnetic Pole during formation, but as continents shifted, their location changed while their directional alignment remained constant.
Well, those were the evidence of rock movements. It's amazing to think that they're happening while we're unaware of. They're slow but steady movements that takes years, decades, centuries, and millions of years, going through different periods, ages, and time. Now that you mentioned different time periods in Earth's history, why not let us find out how Earth's history is written?
From what I've heard, rocks have helped us indicate how old our planet was and how it used to look like. So how about let's start identifying the age of rocks.
Leave us alone!
Determining the age of fossils and rocks is such an important task. From this information, we can accomplish things such as uncovering the past of the Earth or predicting future geological activity. But how do they do it, I hear you ask?
What are you mean?
Well, firstly, remember those stratified rocks we talked about earlier?
Let's say, some time ago, there was a tall mountain and a lake right next to it at the feet of the mountain. Over time, wind and rain gradually chip away at the mountain, and then the bits and pieces chipped away from that mountain tumble all the way down until they drop into the lake. Those particles would float around in the lake and make their way to the very bottom thanks to gravity. There, they eventually settle down and get packed so tightly with each other that they form a whole new layer of solid sedimentary rock at the bottom of that lake. Then, as time goes on, more and more rock particles will follow the same process and start to lay on top of each other like stacked blankets. This entire process is called stratification, and it results in rock formations called stratified rocks that look banded or layered. These layers each represent a layer of particles that once settled and solidified to form the rock formation, and these rock formations are basically a record of the Earth's past.
But how does this help us find out the age of rocks?
Well, you see, these rocks are the very basis of one of the methods of relative dating. As the name suggests, it's a way for people to find out the age of something, specifically a rock, in comparison to other factors, like other rocks. Because of this, it doesn't give an exact value of a rock's age. Instead, it simply tells whether or not a rock is older or younger than another rock. Now, let's think back to those layers. The layers at the very bottom of the stratified rock formation is the oldest and was the first layer of sediment to have solidified. As you go up the formation, the layers get younger and younger. This is how you can tell if one layer is older than the other. And this basic principle of relative dating is called the principle of superposition.
Huh? Look at these. These stratified layers are weird and wiggly.
Well, since various geological events can happen throughout the lifetime of those rocks, a lot of stratified layers look like they're warped or broken apart. There are even geological principles for those. These warped layers were actually originally straight, but events like faulting or folding warped them and turned them wiggly. This is the principle of original horizontality. Because of water erosion with rivers forming and the formation of fault lines, these layers look like they're separate, but they're actually one continuous layer. This is the principle of lateral continuity. There are also these layers that look like they cut through other layers, but remember that these layers are still younger than the layers they cut through. This is the principle of cross-cutting relations.
But this is just to tell if something's younger or not compared to something else. How do we actually get a number?
Well, my friend, if you want an actual number, then look no further. Absolute dating methods are used to get an estimate of a rock or a fossil's age. One such method of absolute dating is called radiometric dating. See, various trace radioactive isotopes can be detected in various rocks, and these isotopes decay over time and gradually transform into other isotopes. The rate at which they decay is measured by its half-life, which is the time it takes for a group of those isotopes to decay by half. Different isotopes have different rates at which they decay, and those isotopes decay as the rock ages. So by measuring how much those isotopes have decayed into other isotopes, you can get a number estimate of that rock's age.
And from these different methods, scientists and bright minds alike have constructed a timeline of the Earth's past, also known as the geological time scale.
Let's get out of here!
Now, for the geological timescale. The geological timescale is based on the idea of dividing time from the formation of the Earth to the present day. It is a system used for organizing the Earth's history into units of time. The largest unit is the eon, which is further subdivided into smaller units such as eras, periods, and epochs. Each unit represents a significant change in Earth's environment or life forms.
How did they make these different time intervals? And how did even humans know about this when they didn't even exist at that time? And what happened during that time?
Just like mentioned earlier by Felix, scientists use dating methods on rocks and fossils to make the geological time scale. They mark the start and end of different time intervals by looking at the appearance and disappearance of different species in the index fossils record.
Oh, so what are the eons in Earth's history?
There are 4 eons in Earth's history: Edian, Archean, Proterozoic, and Paleozoic.
Oh, so what happened during that time?
A lot of things happened back then, but here's a brief summary.
During Hadean, Earth was subject to frequent meteor impacts and intense volcanic activity, and it is believed that the first oceans formed. Archean, this is where the first microorganisms appeared. Proterozoic was characterized by the emergence of early life forms and formation of the first continent. Paleozoic, this is where the evolution of multicellular life forms and the development of the first animals occurred. Just like mentioned earlier, all eons are further subdivided into eras, periods, and epochs. One example is the eras in Paleozoic eon, which are Paleozoic, the Mesozoic, and the Cenozoic. Paleozoic, the emergence and extinction of various animal groups, and this is also the era where supercontinent Pangaea formed. Mesozoic, also known as the age of reptiles. This is where dinosaurs dominated the land and also saw the appearance of mammals and birds. Cenozoic began 66 million years ago and continues today. This is also known as the age of mammals. This is where mammals diversified and became dominant animals on land. This is split more into periods and epochs.
This is getting crazy. Where's the exit?
Geologists are people who study or discover rocks and minerals.
While pumice is the lightest rock element of Earth due to its porous structure.
Obsidian was used back then by tribes due to its extreme sharpness.
Jadeite is currently the most expensive mineral in the world.
There are 8 rocks from the moon that's available to touch for the general public.
They're everywhere. Let's go! Go away!
Hey, what are you two doing out here? I think the dismissal is already an hour ago.
What happened? That's when there were people right there. Yeah, they're crazy. They told us about weird stuff about rocks and...
Okay, that's enough. I think your parents are a bit worried about you here in our school, so you should go.
Man, what a crazy day.